So today what we will do is try to actually make a mathematically rigorous analysis of the laminar premixed flame problem. What we have been doing so far is somewhat like a phenomenological construction of energy balance and mass balance, looking at the preheat zone and the reaction zone separately. In fact, we went all the way up to even considering not only upstream diffusion of products and consequently a downstream reduction of reactant species concentration relative to the far upstream reactant concentration. We also took into account the effect of non-unity Lewis number of the reactants in trying to find out how the reactant concentration profiles are going to change because of that. But however, when you are now doing the rigorous analysis, we start with the Schwabs-Zeldovich formulation, which means we have to go along with the 11 assumptions that are attendant to the Schwabs-Zeldovich formulation, and then we make further assumptions, hopefully only a few, that is particular to this problem. So further assumptions. The first thing that we make is a somewhat a peculiar simplifying assumption which could be relaxed. Number of moles does not vary. During the reaction. So let us suppose that we have Na equals Nb equals N, and this corresponds to saying, so for example, for a I shouldn't say N, or for a let's say nth order, or should say maybe we just go with N. For nth order rearrangement reaction, such as, like, let's say Na equals Nb B, when you now say Na equal to Nb, then this actually implies that Wa equal to Wb. So what basically happens is your mass fractions and mole fractions are equal, so you don't have to worry about a further equation that relates to mass fractions and mole fractions. Second is we assume a calorically perfect gas. Now notice that we did not make this assumption as part of the Schwabs-Zeldovich formulation. We could still deal with a integral T reference to T CPT CPdt in the case of Schwabs-Zeldovich in general. That means you could assume a temperature varying specific heat, but here we make a calorically perfect gas assumption, that is Cp equal to constant. Also, essentially we are saying all thermal properties are constant, K is a constant. So let us assume that the thermal conductivity is a constant as well. Number 3, flame is one dimensional and planar, and steady. Of course, steady state is assumed in the Schwabs-Zeldovich, but just we want to point out here that we are looking at a steady flame which is one dimensional and planar. That is the assumption, which is not very unrealistic. If you think about, for example, if you had a slotted Bunsen burner, you could actually have a conical flame, and locally along the side of the cone, or I shouldn't say conical, like a tent shaped flame, and locally along the side of the tent, like the shoulder of the flame, is reasonably planar. Of course it does not look one dimensional, but we will notice later on that we should be able to actually take a component of the flow perpendicular to the flame and then treat the flow field across the flame locally like the way we are doing here. So that this is a very reasonable assumption. The other ones are obviously simplifying assumptions. So let us now proceed with how we would do the Schwab-Zeldovich. So the Schwab-Zeldovich energy equation goes like, take a divergence of rho v vector integral t superscript naught to t Cp dt minus rho d gradient integral t superscript naught t to t Cp dt equal to minus sigma I equals 1 to n delta HFI naught Wi is what we had. We denote negative sigma I equals 1 to n delta HFI naught Wi as, let us say, WQ. Alright. Now that is kind of like a summation is equal to like reaction rate times the heat of reaction. Of course we are assuming a single step reaction as part of the Schwab-Zeldovich formulation. Of course this was not the final energy equation that we derived in the Schwab-Zeldovich. This is what we had actually termed as the Schwab-Zeldovich energy equation while we were doing the formulation. So it is basically taken right from there. We haven't formed the coupling terms or the alphas and all those things at this stage, but let us suppose that we can just proceed from here and then apply the one dimensional apply this to one dimensional situation. Then here we can now write this as rho u d by dx of Cpt minus T naught minus rho d squared over dx squared Cp T minus T naught equal to Wq. Okay. Essentially the divergence has become like a d by dx, and for a one dimensional flow we know that rho u is a constant. Therefore we can actually pull this out because rho u is a constant. We are together as a product, we can pull that out of the derivative, and then we evaluate the integrals for a constant Cp, and we also do the same thing over here. And since it is one dimensional, we can write it as a ordinary derivative instead of a partial derivative, because things are varying only along x, which is in this direction across the flame. Okay. Then we write the Schwab-Zeldovich species equation for species A. Let's say that is the reactant there, and so we now write for this species. Now what you will find when you now try to apply the Schwab-Zeldovich formulation is we don't necessarily solve the entire n plus 1 equations that we talked about, where n is the total number of species involved. Okay. Although it looked like they were all coupled and we have to solve them simultaneously and so on, what we are actually looking for is for equations to look identical. So if equations begin to look identical, then it is sufficient for us to solve one of the equations that are that's a part of the identical set instead of having to solve for all the equations simultaneously. So this is how we simplify our lives instead of actually burdening ourselves with lots of equations to solve. So here in the case of the premixed flame, we will see that for the moment it is actually sufficient for us to take the species A conservation alone. We do not have to worry about lots of other species. So here you have a divergence of rho v YA minus rho d gradient YA equal to WA. Now since you have same number of moles everywhere, we can point out that WA equal to minus WB equal to minus W, right. So WB is the rate of production of B, WA is the rate of depletion of A, and so rate of depletion of A should have a negative sign to denote the depletion. If you are now writing it in terms of the general reaction rate W on a mass basis, so here if you now try to unwrap the divergence and vector notation and so on, fortunately we do not have an integral to evaluate in this case as in the energy, so it should simplify as d by dx of YA minus rho d d squared YA over dx squared equals minus W. As a matter of fact, I should point out that we are also assuming the rho d to be constant, by the way. That's not, that's sort of implicitly stated here because we are assuming d to be a constant, and this is like an incompressible flow where the mixture density does not change, so therefore and then of course we are not even bothering about the mixture density changing with temperature, alright. Therefore we would actually suggest that rho d is a constant, and we can go through with the divergence all the way to the applying the gradient, and therefore you get the second derivative here. Alright, now we want to actually try to see if these two equations are looking alike in some way, and this is what we also tried to do when we did the Schwabs-Zeldovich formulation anyway, right. So here if you denote theta equal to Cp T minus T naught divided by Q, and alpha equals 1 minus YA. This is pretty interesting actually, because well this is kind of obvious. We want to get the Q down here, we want to get the Q down here, okay, and then you have essentially T is the one that is varying, Cp is a constant, T naught is a constant, but you have this T with all this paraphernalia like Cp times T minus T naught together, and then okay, so we want to now say that's like the variable now instead of the actual variable temperature, and then we get this Q down here so that it will also have a W just there on the right hand side, just as well as the species equation, but the species equation has a negative sign for the W. Therefore if you want to have only a W there, all you need to do is to actually multiply this by a negative sign on the left hand side. That means we should have actually been saying alpha is equal to minus YA, not 1 minus YA. So why were we looking at 1 minus YA? This is a trick, okay, that is not really highlighted in textbooks and so on. What we are basically looking for is something physical. Look at how we actually proceeded in the phenomenological development of the structure of the premixed flame. That was the key. We noticed that the temperature profile goes like this, and then we started asking questions about how would the product profile look like, right, and then we came to the conclusion that if most of the products are actually produced here, we should anticipate that the product concentrations should actually grow only over here, but once the products are actually formed, they kind of look around and see, hey, I am actually a lot over here and I am getting convected down there, so I am also there. The only place that I am not here, not around is here, therefore can I diffuse, but I am getting convected down. So there is like a balance of how much upstream diffusion the products can do versus the downstream convection that they experience, and that would actually give rise to a concentration profile that becomes pretty much identical to the temperature profile in the event of a Lewis number equal to 1, which is assumed in the Schwabs-Zeldovich formulation, right. So then we realize that the product species also goes through a convective diffusive balance in what we thought was the preheat zone for only the thermal balance earlier, and so we anticipate that the product concentrations should look pretty much like the temperature concentrations if you normalized in certain ways, right. So how would you normalize? Like this looks like a normalized temperature in some sense, not exactly T to the superscript naught, which is the standard temperature. We should have actually put T to the subscript naught for the initial temperature, then this would have looked like a normalized temperature, and I will come to that pretty soon. But this one, instead of just saying alpha is equal to minus Ya, which would have done the job for us here to actually make this look similar to that with T replaced by theta through this transformation. We are actually saying 1 minus Ya because alpha now begins to actually act like the product species concentration, right. So it's essentially saying whatever, so if I had only two species, let's say, okay, A and B, and then you can clearly see that YB would be like 1 minus Ya, right. If you had multiple species, it didn't matter, finally you are going to actually have something that out of which you are subtracting Ya, so 1 minus Ya will do the trick for you to actually have alpha go more like the product, you see. So that's essentially the idea here. So we are actually looking for the equations to look similar by choosing a if you want to call it a transformation, by choosing a transformation for the species reactant species concentration that will mimic the product variation, because that's how we actually develop the phenomenological understanding on how upstream product diffusion causes a downstream reactant depletion through diffusion. So yes,
the pressure remains constant in the flame, and we have taken rho to be constant, so how is temperature varying?
yes, so that's a the effect of that is going to be felt in the flow. Okay, so what will happen is if you really have a density that depends on temperature, then your mass balance is going to get affected. So your when you say that rho u is equal to a constant, if the rho changes with temperature, your u is going to accelerate, right. That is something that we noticed in the Rankine-Hugoniot formulation, that across the deflagration the flow accelerates, right. So 1 over rho u increases, so rho decreases, and therefore T should increase anyway, and then u will also increase. All that stuff is correct, but in the Schwabs-Zeldovich formulation we are actually adopting a given flow field, and the given flow field here is a uniform flow field. That means no matter what the constituents of the mixture are, or what's the composition of the mixture is, as we go from the reactants to the products through the flame, the mixture as a whole is having only the same velocity. We are ignoring the fact that the flow is going to accelerate. It's as if like we are not interested in it, we are not worried about it, okay. For correspondingly, then we can actually go with a constant density situation, or we don't explicitly state that we say rho d is a constant, and then we start thinking about why should d vary with rho in a way that rho d is constant and so on. That's not exactly the way it is justified, okay. So the way it is justified is we are basically thinking about like an incompressible mixture, and we are violating the gas law, the perfect gas law, but that violation is more felt downstream of the flame when our business is over, so we don't worry about it, okay. So this is something that I pointed out that right at the beginning when we are doing the Schwabs-Zeldovich, or when we actually did the one dimensional momentum to show that it will reduce to something like pressure is approximately equal to a constant. The point there being, if you want to take into account the velocity variation in the flow, then only then you have to worry about the density variation with respect to temperature, and then the flow problem and the combustion problem will get coupled. Here we are actually looking at a combustion problem that's decoupled from the flow problem, for which we have to make this assumption. Okay, so if you now go back and plug theta and alpha in the energy and the species equations respectively, you now get equations that look like rho d squared theta divided by dx squared minus rho u d theta over dx plus W equal to 0 and rho d squared alpha divided by dx squared minus rho u d alpha over dx plus W equal to 0. Hey, those two equations look exactly the same except that one of them has a theta, the other one has an alpha to solve for, right. Now if you were Greek you might have a preference of theta over alpha, but I am not, so I am not going to really worry about which equation I am going to solve. Is that okay? Is it okay to say now it's sufficient for us to solve only one equation? We don't have to solve both the equations, or what is the catch? Would theta and alpha look exactly the same as you solve for one and then expect the other one to behave exactly the same? Is that okay? Fine. Whenever you are confronted with two differential equations that look identical except for the symbol that is used for the independent variable, also the dependent variable, I am sorry, or as a matter of fact, okay, independent variables, okay. So or the two equations go and actually give the same result, or what are we missing? There is one more thing that we have to worry about. All differential equations have the burden of having to satisfy boundary conditions, okay. So at this stage we can say that theta is going to be related to alpha if it is, and it is sufficient for me to solve one equation and get and then satisfy its boundary conditions and obtain one of them, let us say theta, then I should be able to say that theta is equal to A alpha plus B, alright. And why would I say A alpha plus B? Because I am expecting to have two boundary conditions for alpha as well, with which I can actually evaluate A and B instead of having to freshly solve this equation for alpha and then apply its boundary condition. So that would actually give me room for applying boundary conditions for alpha. Or before we proceed in that direction, we are probably better off looking at what are the boundary conditions for theta and alpha and see if they are also identical, right. If they are identical, then what do we say? Right. So let us see, and it isn't terribly unrealistic to expect them to have nearly identical boundary conditions, because as I said this is mimicking the product, and in the case of unity Lewis number we expect that these profiles should be the same, right, if these things have been normalized right, alright. So hold your breath, okay, hold on to your seats, we are going to have some fun here, right. So let us look at the boundary conditions. Cold boundary that is x equals minus infinity, alpha is equal to 0, theta equal to 0, assuming, supposing T superscript naught as T naught without loss of generality. Because I could have actually written this as T minus T subscript naught minus minus of T minus subscript T subscript naught plus T subscript naught minus 2 superscript naught. So I could have added and subtracted my actual temperature initially. That's essentially saying I have a sensible enthalpy initially above the reference value for the reactants, that is now going to be added up over here, which is a constant, and therefore it is not going to really affect me at all. So I could actually say that effectively T is whatever it is, and then say theta is equal to 0 and alpha is also equal to 0, because I am assuming that I am going to have all of them as reactants upstream, and then alpha Ya should be equal to 1, and hot boundary x equals plus infinity, right. Now theta will now give you Cp Tf minus T naught divided by Q, and alpha should be equal to Ya goes to 0, all the reactants are getting consumed in the flame, and therefore you are going to get alpha to be equal to 1, but what is theta? You get this funny expression there. Can we evaluate it? That's equal to 1. Okay, that is because of the adiabatic flame temperature. In the case of an adiabatic flame temperature, this is the heat that is released in the chemical reaction, and all the heat that is released in the chemical reaction goes to increasing the sensible enthalpy of the mixture. That is what an adiabatic reaction flame is all about. Okay, so CpTf minus T naught is a sensible enthalpy rise of the mixture, which is primarily coming from Q, and therefore this is also equal to 1. Lo and behold, the boundary conditions are also identical. Wow, we made such a big fuss about 4, 5n plus 6 reactions in the combustion problem, and then we now belabor a lot to get the Schwabs-Zeldovich formulation going, and we still had to get stuck with n plus 1 reactions, n of which were fortunately homogeneous and all those kinds of things, and finally we are able to actually get to 2 reactions that we just pick out of them, and then we find that both of them are identical and the boundary conditions are also identical, therefore it is sufficient for us to solve only one equation. Great progress, right. So therefore, considering one equation is sufficient. If you were to still persist and say, well, theta should be equal to a alpha plus b, and you can substitute the boundary conditions for alpha and then plug in values of theta and alpha, there you will find that a is equal to 1 and b is equal to 0, alright. So then you will be able to show that theta is equal to alpha. So that's mathematically showing things. Okay, so what we want to do now is get confronted by that 1 and 1 equation. Let us say we take the one that is written first, right, and then we want to deal with this, and we want to see how to solve this, right. For the first time in our lives as combustion students, we are going to solve something. So far we have been only posing problems. Okay, oh my god, how do I solve this? What is the problem? That is a second order ordinary differential equation with constant coefficients, as a matter of fact. Okay, rho d is a constant, rho u is a constant, okay, and then you have a it's an inhomogeneous equation, all right. Okay, what is the inhomogeneity all about? You have the W, that is the chemical reaction rate, and you have the theta there through the temperature sitting on top of an exponent with a negative sign, right, sitting in the denominator on top of an exponent with a negative sign. Okay. So that is the ugly looking expression that has been camouflaged by a simple W there, you see, and that has been the one that we have been really feeling jittery about all these years, and there we are, we have to solve. So how do you do this? Chicken out of the problem. Say, well, can I look at the flame where you don't have a W? Right? Yeah, sure, of course. So you get into the flame, you now with a lot of trepidation you get into the flame, and then still no W. Oh sure, fine, this looks great. So I get in there and then no W at all for quite some time. So I can solve that. Can I? So what we would do is we now begin to notice the way we were talking about things earlier, that you have a flame with a preheat zone with hardly any W, where I could actually go ahead and jolly well solve this, and then I have to look at this region where I have to confront the W and then point out that you pretty much have nearly the same enthalpy for the incoming species and the outgoing species, so you don't really have a convective enthalpy flux to worry about, and therefore I am going to get rid of this, right, and I am going to look at a reactive diffusive balance and then try to integrate that, right. Why, I mean, we still have to take this W into account ultimately, so what's the big deal? The answer is, what is it that we are actually looking for out of this equation? Can we now find out what exactly our problem is? What is the one single quantity that we are trying to solve for? Do you know what the problem is in our lives? We don't know the flame speed. Okay, so although this is like a very innocent looking constant that's been pulled out, we don't know what the U is, right. So what this actually allows us to do is, we can say, while I am actually in the convective diffusive balance, I keep the U, which is what I don't know, right, and then it turns out to be like an eigenvalue problem. So an eigenvalue problem is where you have one of the coefficients that's an unknown and you supply the boundary conditions, and then you turn out that the boundary conditions aren't sufficient enough for you to actually evaluate the eigenvalue, right. So in this case what you do is you retain this in one of the regions and you get rid of it in the other region where you have to confront the W. So you are kind of breaking your problem into two parts, divide and rule, right. This was my problem, this was my unknown, keep the unknown, get rid of the problem in one, and keep the problematic thing and get rid of the unknown in the other. I should be able to handle this, but what's the catch? I solve for the, this is going to still need two boundary conditions because it's second order, right, and my zone is only from here to here, right, and strictly speaking I don't know exactly where to draw this line, alright. It's sort of like as I keep on entering into this region and then the chemical reactions are happening somewhere, I suddenly feel too hot and then say, I think I have got into the reaction zone. So it's a feel, right, I don't know exactly where it is and I need a boundary condition there where I don't even know where the boundary is. Okay, and look at this part, right. If I now want to keep this and that, I still am not throwing out the leading order term, which means I need to have, it is still second order equation and I need two boundary conditions, and the boundaries are this fuzzy boundary somewhere here and the far downstream boundary. Okay, but all we have stated so far is I knew what the boundary condition is here, I knew what the boundary condition is there. So what do we have to do here? We have to now come up with two boundary conditions because it's second order which are shared by these two. So that's what is called as interface conditions. So that's an interface between two zones and we have to supply two conditions that are shared by these two. Okay, and whenever we are looking for two conditions, it's because it's second order, and if it is second order then we are looking for two conditions, one in the value and the other one in the first derivative. And in fluid mechanics the first derivative mostly has some significance in the sense the first derivative is going to actually deal with the heat flux, the value itself is going to be on the temperature. Okay, so we will go through these steps rather quickly in mathematical way. So region 1 is our convective diffusive balance, right, convective diffusive zone, which implies that W is approximately equal to 0 and then we can write d squared, we can go back to t, don't worry about theta anymore, that was just to show that theta and alpha are the same. You can go back to an equation that's over there. So d squared t over dx squared minus rho u cp over k dt over dx is approximately equal to 0. Now when you say this is approximately equal to 0, this equation is what is called as the 0th order equation. So what we are actually doing is a part of a larger approach called asymptotic matching, okay, or what's called as matched asymptotic expansions. Strictly speaking, what we should say is the temperature profile can be expressed as an asymptotic expansion, alright, and we now try to take the what's called as the 0th order, where whatever is actually a small quantity in the equation is set identically equal to 0. It is not exactly 0, right. You do have the temperature rise and you strictly speaking have a reaction rate that is beginning to increase. Fortunately for us, if the E is large, it is going to get confined to a smaller region, okay. So that is what we are really counting on, but it is approximate. So to leading order, to 0th order, we now set it identically equal to 0, get rid of it from the equation. In the first order we have to refine the equation with keeping that small value, you see, we will not do that fortunately, okay, we will not do that, we will just do only the 0th order matching. So let's call this equation 1, and the boundary conditions here, as we talked about, we want to retain the cold boundary conditions, which is T equals T naught and x equals 0 minus. So we are now locating our x equal to 0 at the edge of the preheat zone, reaction zone match, and we want to call this x equal to 0 minus T equals Ti. Many times we are tempted to think that I stands for ignition temperature, okay, and then we were always looking for what's called as an ignition temperature. That is like a popular notion, and it's a popular engineering notion to think about like an ignition temperature. Mathematically speaking, we have to confront a cold boundary difficulty that you have reactions happening even there, okay, it's just simply not significant enough. As far as here, Ti is unknown actually. It's not like we are going to plug in a value there that's above or that's somewhere in between the room temperature and flame temperature. That's not what you're going to do. It's an unknown. It's a temperature that's going to be shared as the upstream boundary condition for the reaction zone, alright, and it's an unknown. So that's region 1 for you. Region 2 is reactive diffusive zone. Here what we then say for the 0th order reaction is d squared T over dx squared plus W cube over K is approximately equal to 0. That means this is the diffusive part, this is the reactive part, the balance is essentially that. You hardly have any convective flux that's going on, that's changing. So you don't have a, essentially what that really means is you don't have a dt by dx significantly, okay, that's a very small quantity. So the boundary condition here, we can easily write the hot boundary condition, which is x equal to infinity. We can say T equals Tf, that's like what we had started with, but then the interface condition is x equals 0 plus, we have to write the same, T equals Ti, which is an unknown, right. Now if you are really a little bit more careful, you would probably want to write this equation for the region 1 as d squared t1 over dx squared minus rho u cp over k dt1 over dx, and then write these as t1 equal to t naught and t1 equal to ti. You can say here you can plug in a t2 and then t2 t2, and then finally say at the interface t1 should be equal to t2 and so on, okay. But we understand that ultimately it's going to be a single temperature profile that we are interested in. And then we said that we wanted to have one more boundary condition at the interface that needs to be shared, and since it's a second order equation, we can go up to the first order. The first derivative is signifying heat flux, and therefore what this really means is matching heat flux at the interface between the two regions we get dt over dx x equal to 0 minus should be equal to dt over dx x equals 0 plus. Well, strictly speaking we should say k dt by dx, but since it's the same species and as you now go to 0 from both sides, it's essentially the same location, the k's are the same, so we don't have to worry about it. But these gradients are coming out of two different solutions, and we are actually trying to force this is going to say that we are going to force these two solutions to have the same gradient at this point. What that really means for you is, keep in mind what we were talking about for the length scales, characteristic length scales for thermal balance in the preheat zone versus the species mass in this zone. When we were looking at non-unity Lewis number the other day, we pointed out that if you were to just bother about the Schwabs LH only here and then take a equation that looks like this with a 0 on the right hand side, you can actually solve this, but what you will find is you will get a solution that kind of goes like this and then goes exponentially there. For x greater than 0, which is not the domain of validity, it's outside the domain of validity of this equation, if you were to extend the solution that you're going to get from there for your t1 of x, you're going to get a solution that goes exponentially, right. That's what a second order homogeneous equation is going to look like. You try to solve this, you will get exponents, right. So you will have this. On the other hand, what we are talking about in this equation, this is also something that you can solve. What you will find is this is going to actually give rise to something like that, and what we are saying is at this place we want to have the temperatures as well as the slopes match, and that's where we want to position our x equal to 0, somewhere there, right. So this is typically how we want to construct the composite temperature profile in a composite manner, by having this asymptotic matching. What you're doing here is a zeroth order matching, strictly speaking, because we are identically setting whatever is a small quantity in the equation to 0 and solving for it. So this is the problem, and out of this we are trying to get the velocity u. We will do the first region and then hold on till next week for the second region with bated breath, I hope, right. We can't wait to get there. So of course we say that this equation is 2, and what we want to do is integrating 1 once, right. We say dt over dx equals rho u divided by k cp t plus a constant, and we have to supply a constant of a boundary condition to satisfy to evaluate this constant of integration. One way of doing this is to actually integrate it twice, and then you now deal with two constants and then apply the boundary conditions, right? But I am not going to do that. What I am going to look for is, I am actually interested in dt over dx at 0 minus, okay. So I am not really interested in going ahead with integrating this twice to look at actually the temperature profile. This is a point where the analysis sort of cheats you, okay. So until now we have been talking about these profiles matching and all those things. We are actually going to we are going to think that we will get this matching and get this composite profile, but typically at this stage the analysis abandons its care about the temperature profile. It now starts bothering about the velocity, which is the eigenvalue, right. That is what we are really looking for. So we do not really want to care about getting this and I am stating this explicitly because textbooks do not state this explicitly, and then when you go back to laminar flame analysis to actually look for the temperature profile, you will not find it there. Okay, and then but they are like let's just go through this and then get the velocity, put a box around, then we got laminar flame speed, let's talk about the laminar flame speed and just keep going on. Okay, so you never really get unless you go dig up literature further, you can't get this temperature profile. So that's a kind of attitude that you're going to get. So since that means we now have to actually evaluate what the dt by dx is far upstream. So since we are saying that at far upstream in this region 1 t equals t naught at x equals minus infinity, then t equals t naught for quite some distance there, therefore the dt by dx is going to be equal to 0, x equal to minus infinity, t equals t naught, dt by dx equal to 0. This is asymptotically approaching, that is the reason why we are able to actually reduce this, otherwise we can't, okay. So that means dt by dx equal to rho u divided by k Cp t minus t naught, right. Now if you think about it, this is the first thing that we wrote in the phenomenological balance. We said that rho u Cp is essentially your rho u Cp t minus t naught is actually the enthalpy rise that is happening, and that is because of the heat conduction k dt by dx, and we approximated it as k t minus tf minus t naught divided by delta. That is what we did earlier, okay. So whatever we could actually write by just looking at things, if you think about it, takes about an hour for you to get if you go through the mathematics, alright. And there we are, so that is what we got. Now therefore if you want to now apply this to the other boundary, we now say at x equals 0 minus, this is equal to rho u Cp divided by k Ti minus T naught. Here we are imposing the next boundary condition, and then what you are going to say here, and or maybe this is a good point to stop, okay. So we will just say this, we keep in mind we do not know what Ti is, that is an additional problem that we have to worry about, and we will see how to handle this next class.